Today I will begin again with the quantum mechanics portion where we had left off the last time. So this is part of a review and introduction to the whole topic of quantum mechanics. As I mentioned, the course will not go into great detail in that. Either you have already studied it, or if you need it, you'll have to pick it up later. But the course cannot dwell completely on quantum mechanics. So we'll continue with where we left off after describing that light can behave both as a wave and as a particle. Then we had ended up with the idea that the electron could also behave as a particle, which we are more familiar with, or as a wave. And the equation that connected these two behaviors was the de Broglie equation. And we left it at that point, basically. Now, to understand the wave-like behavior of matter, or what we might refer to as matter waves, if matter is treated as a wave in its behavior, there is an equation that is very fundamental, and that is called Schrodinger's equation. Now, Schrodinger equation is not something that we can prove as such. Basically, it came out of that guy's head, and is the best equation that explains all that we can observe at this atomic level. Okay, it's a model that best fits the observations, including the quantum behavior at an atomic level. So what we're going to do is not to sit and try to prove Schrodinger's equation, that is anyway beyond the scope of this course, but to see some key points that will allow us, when we go into the topic of understanding the electronic behavior of solids, how the quantum nature, the classical nature we saw, Drude's theory and so on. So now what we'll do is just have some concepts which you already are familiar with, reviewed to bring us to understand the quantum behavior of solids. We can represent the electron wave by a wave function. Right? And the wave function is represented in one dimension as psi, as a variable, as a function of x and t, excuse me, in one dimension. And if we talk of 3 dimensions, then we are talking of x, y, z, t in 3 dimensions. All right? The important thing to remember is when we are trying to understand what this is that psi itself has no physical significance. So don't try to imagine what psi is like. That's, I think, futile. But what is more important physically is psi squared. Okay? So that will have a physical significance too, which we can picture and work with, but psi itself has got no physical significance. The square of the amplitude, okay, if we take psi and we take the amplitude squared, okay, that gives us the probability of finding the electron per unit volume at a time t. Okay, at a specified coordinate x, y, z. Remember, we had defined psi as having x, y, z and t coordinates, and so the amplitude squared gives us the probability of locating the electron at any position x, y, z at a time t. Alternately, if I expand that to give its fullest expression, we can also write dx, dy, dz as the probability of finding it in an elemental volume dx, dy, dz at time t. All right? So this was the probability of finding it at a position x, y, z at time t. This gives me the probability of finding it in an elemental volume given by dx, dy, dz at any instant t. Okay? And so if we normally leave out, we would work with time-independent cases. In one-dimensional, when we work with, we write psi. If we are considering time, then the x dimension and t is there. If we are looking at the time-independent case, we have only x. All right? So the probability that we have in one dimension, this is the three-dimensional case, the probability in one dimension similarly is for finding it between x and x plus dx at time t. So these are the various expressions that we will make use of. All right. I'm sorry, dx will be there. Yes, you're right. There is a dx term here. Psi, the amplitude squared dx, is the probability of locating it between x and dx at time t. In general, this term psi need not be restricted to real numbers only. It could have a imaginary component. In other words, psi may be complex. So in that case, what we are representing here as the amplitude square will be written in terms of the complex conjugate psi star psi. Okay? So if it is complex, then psi star represents the complex conjugate. So this is the more general expression when you are considering amplitude, because what we have here limits us to the expression of real numbers, but there's no particular reason why the wave function has to be purely real. Including the imaginary parts, we express it in terms of its complex conjugate. Now, we can try to set up the Schrodinger equation. Let us suppose that an electron has a potential energy V given by V is equal to Vxt. And for time independent cases, excuse me, we would have V is equal to Vx. If E is the total energy of the electron, then what we have is the time independent Schrodinger equation. As I said, this is not something we are attempting to prove. Okay, I'm just abbreviating Schrodinger equation as SCH there. Will be given to us by d2 psi by dx squared plus 2m by h bar squared E minus V psi is equal to 0. Okay? We can write psi x because we have separated out the time dependent part. This is only describing the psi x part of it, describes only the spatial behavior because we are considering the time independent case. Right? And in this equation, m is the mass of the electron. So this equation that we have here is referred to as the time independent Schrodinger equation. And in books and courses that deal with this, your first thing will be to try to solve this for particular cases and so on. And in general, the solution of this for any real material is a rather complicated task. And so typically you will describe specific models, very, very simple models, and solve it. And then you may say this is then extended to 3D and so on. Okay, that is generally the approach that is taken because it's rather complicated. I won't even bother to go through the whole solution. I will simply say that the solution depends on certain boundary conditions. So I'll just give sort of the results more or less what we will need rather than the actual solution on what are called boundary conditions here. Basically, the boundary conditions specify the limits within which we are operating, right? That's what we mean by boundary condition. It has to satisfy these conditions because we know, say, from either some externally imposed physical reality that it has to match at this point some condition, at some other point some other condition. And so that gives me a certain set of conditions that this equation has to satisfy for certain values of x and so on. So boundary conditions, what we specify, are very, very important in the solution. Now here are some possible boundary conditions that we use. One is, first of all, that psi must be continuous. All right? And the implications of that is that a function which looks something like this is not acceptable as a solution for this equation. There is discontinuity there. So we cannot use this as an example of a wave function that is acceptable here. The second is that d psi by dx must also be continuous. Okay, if that is a plot of psi versus x. In this case, then, an example would be that something like this, while being continuous, okay, the function is continuous, but d psi by dx is not continuous. So a function that has some shape like this will also not be an acceptable function as a solution for this. Already from these boundary conditions that are being set up, we have some limits set on what are the possible types that may be there. A third is that it must be single valued. That arises from the fact that the amplitude squared, which is my probability, cannot have more than one value, since that represents the probability of finding the electron somewhere. Right? So if psi has more than one value, then at the same point in space or in a certain volume, there are multiple probabilities of finding it there. And that doesn't make sense, physical sense. So that is where this is coming from, that it must be single valued. And by that we mean that a function which may look like this, let's say something like this, where there's more than one value for a given x is not acceptable, or a loop, something like this, where again we have more than one value. So some functions are automatically excluded from the realm of solutions by these boundary conditions that are set up. And so only the acceptable wave functions that satisfy these boundary conditions are referred to as eigenfunctions. All right. So because of these boundary conditions, only some functions are acceptable, and these are called eigenfunctions or characteristic functions. Because these refer to steady state situations. They are also referred to in these cases as stationary states. So those eigenfunctions, whatever may satisfy possible solutions, are given, they are called stationary states. And what this eigenfunction does, it specifies the energy, it allows me to specify the energy of the electron. So if I know the eigenfunction that is allowed, then I can also determine the energy of the electron that is allowed. And it turns out that Schrodinger's equation can be applied to all the forms of matter. The solution of it may not be easy for all forms of matter, but the application of Schrodinger's equation in this form applies to all forms of matter. Let us consider a specific example of what might be called the electron in a well. Again, I'm not going into the details. By that I mean there are two barriers that are infinitely tall, and the electron is located within this. When it is within this barrier, set of barriers like a well, the potential is 0, whereas the barriers have got infinite potential on either side. We say that the space between these barriers is A, all right? And so we have now a situation in one dimension like this. This is the electron that is within the barrier with energy, potential energy V is equal to 0. So in this case, the probability, this is giving me another additional boundary condition here, the probability of finding the electron outside the barrier is what? So this function's amplitude squared is equal to 0 when x is less than 0 or x greater than a, right? And correspondingly, it is non-zero when it is within 0 to a. So we write our equation in one dimension as before. E, the total energy. Now in the general case there was E minus V, right? But in this case for the electron, V is 0 because we are considering it within the well. It is trapped within here. So I don't have a V term there. We simply have E psi is equal to 0.
So V equal to 0 only at the ground state.
Yeah, it is only having that. No, the potential energy, that's not the total energy. The potential energy is 0 for all the states. The total energy, E, will be different for the different allowed energies that are there within it. But V is simply the potential energy, mind you. And it has a kinetic energy component too. So this E minus V term is representing what? The kinetic energy, right? That is non-zero. And even if in the presence of a potential you would still have a finite E minus V, except in this case because the potential energy within the well is 0. So we don't have a V there. But that doesn't mean that the electrons all sit at the bottom there, because they have different kinetic energies, and as a consequence you can have different energy levels. Their total energy is different. But we are considering a single electron in here in a region which has got potential energy equal to 0. Now that's why E minus V simply becomes E. Okay? If you go through the solution for this, what you end up with is E is equal to h bar squared k squared by 2m. My point is not to teach you how to solve this, so I'll refrain from that. We'll simply say E is equal to h bar squared k squared by 2m. So if I want to know how the electron's energy behaves, this is a constant and this is a constant. I want to know what is the behavior of K. Can K have any arbitrary values is the question. If it can, then electron can have any arbitrary energies it wants. It turns out when we look at the solutions that K itself can have only certain values, and we say K is quantized. Quantized means it has only certain allowed values, right? So we will express K as n pi by a. So that immediately suggests where, okay, before I say that, n is numbers, integers, 1, 2, 3, etc. 0 is not allowed. Why? What will become equal to 0? So what?
Psi is equal to 0, psi square is equal to 0, so probability will be 0.
Very good. It's related to the fact that if n is equal to 0, my psi will also become equal to 0, which means the probability of locating the electron within the well is also 0. But I just told you that the electron is in the well. So obviously the probability cannot be 0 in the well. So 0 is not an allowed integer, allowed number in this case. So the implications that K cannot have any arbitrary values translates to also the fact that my E, because E depends on K, cannot have any arbitrary values. And so we write then that En is equal to h bar squared, and then we substitute for K n squared pi squared by a squared, and we had the 2m term from earlier, right? If you go back and look, all we are doing is we are substituting for K here with the expression that we got here, K is equal to n pi by a. And simplifying this, we get then that En is equal to n squared h squared by 8m a squared. Here it is h bar in this part. I have simplified that out so we get in. Okay. So here it's going to be the square of these integers. E1 is then 1 times this number. E2 will become 4 times this, and so on. So now my energy levels are spread as E1 and then E2 and E3 and so on, where E2 is 4 times E1, E3 is 9 times E1 and so on. Okay, so alternatively we can write this as so the energy has also become quantized as a result of the quantization of K, which is the wave number. The lowest possible energy it can have is not 0, we see, right? So this is the lowest possible one. E1 is simply h squared by 8ma squared, and that is what we refer to as the ground state. That's the lowest energy it can have. It's a non-zero value. Also note what is delta E will be En plus 1 minus En, right? The separation between two levels, adjacent levels. And we will get that it is equal to h squared 2n plus 1 by 8ma squared. Okay? So here is the separation. Now for very large objects, the energy level separation when we calculate, we'll find that it is very, very small number, if you can calculate that. So in other words, in those cases, the electron could have practically a continuum. So it is only as we sort of quantize, make it into more small structures, that the separation becomes a significant thing. Whereas when you're talking of large objects, then the electron can behave as if in a continuum fashion, because the separation becomes so small between these levels that effectively it is almost like a continuum, or better still to call it a quasi-continuum, because it depends upon this A term, the size of the well. So as the size of the well becomes larger and larger, this size, the separation becomes smaller. Conversely, as A becomes smaller and smaller, the separation becomes larger and larger. Use is made of this phenomenon in what are called quantum well structures. We'll come to it later in the course. But I can actually grow synthetically on a substrate. I can grow some layers of material, and I can make it in such a way that the layer of interest to me, let us say this layer, is sandwiched in between, say, two other layers of higher band gap. We'll come to all this later in detail. And I can create, and here we are talking of nanometer dimensions, some angstroms. And when I create such a structure artificially during my deposition process, I will see this discretization of energy levels, very, very sharp levels. And that is made use of in lasers, for example. I want a sharp transition, right? So just simply by changing the width of this well, I am changing the separation. So I'm able to play with the emitted light from a laser, from a semiconductor laser, by designing what should be my quantum well thickness. Okay? That's exciting. I can design, I can engineer what light I will get out of the same material, of the same composition, except all I'm doing is simply playing with the thickness dimension. And so it's a very practical application of what we are simply looking at right now. There's another important principle known as Heisenberg's uncertainty principle. It's fascinating to go through the history of quantum mechanics and see how people fought with each other, mostly in a professional manner, occasionally in an unprofessional manner, and where personalities got involved. But these are some of the key people, Schrödinger, Heisenberg, Born, Bohr, Dirac, and how their lives intersected, and finally they argued out some kind of an interpretation which became more widely accepted, whereas somebody else's understanding fell by the wayside. And even today, that is how science is. It's in a state of flux. But Heisenberg's uncertainty principle is probably one of the most misapplied principles. A lot of people like to take it and apply it to all of life and say nothing is certain in life because Heisenberg's uncertainty principle says so. Well, I don't think Heisenberg intended for his principle to be applied to all of life in that sense. But anyway, this is what we have of Heisenberg's uncertainty principle. For a free electron, we have the wave function which represents the wave with wavelength lambda, okay, a traveling wave. Because this wave is extending all over space, it's a free electron, it's not confined, so the wave function extends all over space. And the probability distribution function is therefore uniform. Probability distribution function, PDF, that's like a PDF file format, but it's not the same. PDF, that's a good one. Probability distribution function is uniform. This is the case for a free electron. So what that implies then, everywhere there is a uniform probability of finding this electron. Right? What is the uncertainty in its position? Delta x. What will be the uncertainty of finding this? Since there's roughly an equal probability of finding it everywhere, what can we say about the uncertainty in its position? Very high is, we may put it as infinity. I can't pinpoint, I mean it's got a likely probability of finding it almost anywhere, right? So we say that delta x tends to infinity there. Now when we know lambda for the wave, right, we said it has got a certain lambda, by implication if lambda is known, then p, the momentum, is also known from de Broglie, right? P is equal to h by lambda. So if you know lambda exactly for this wave, then you also know p exactly. So by implication then for the travel in the x direction, which we write as px, let's say, or delta px, what is the uncertainty? Okay? This is the case for a free electron where delta x is infinity and delta p, x, subscript x, for traveling in the x direction is 0. Now consider the case that we were looking at area for the electron trapped in a well. It's a one-dimensional well, okay, infinite, as we saw earlier. In this case, my wave function extends from x is equal to 0 to x is equal to a. This is the case that we just saw. So what's the uncertainty in delta x?
So it's 0 for between x equal to 0 to x equal to x.
Uncertainty in delta x. I got this barrier, this is x. So I will always find it here, right? Or will it be here?
Delta is between the
But I want delta x at any given point. What is the probability? Uncertainty. Is it always going to be found at a fixed point in x? It will range between these two, right? So my uncertainty is it's going to range between 0 to a. So I have an uncertainty of a in locating. It's somewhere between 0 to a in that distance. I can't pinpoint its position and say it's always going to be at this value of x, because it's not. There is a probability of it being 0 to a. Now in the case of momentum, px, it is given by h bar k, or minus h bar k. It can be, depending on how it is traveling, the momentum. It could be plus or minus this. So what is delta px?
H bar A.
Now these are the two values within which it could be. Twice. It lies between a value of minus h bar k or plus h bar k. So we get 2 h bar k is the uncertainty in momentum. Earlier we saw that k was equal to n pi by a, from which I can then get that delta px is equal to twice h bar pi by a. N pi by a, sorry. Okay. Delta px is equal to twice h bar n pi by a. And then you can combine these two, delta px times delta x, what we had, often is the form that which Heisenberg's uncertainty principle is expressed. It's going to be greater than h bar when you multiply those two together. Okay, it will always be greater than h bar. This expression, that the product of the uncertainty of momentum and the product of the uncertainty of, with the uncertainty in position, will always be non-zero. You can't specify both of them exactly. Finds expression also in other ways for other quantities as delta E energy, delta T time will also be always greater than or equal to h bar. What it doesn't tell me is I will be able to tell maybe delta py exactly. So in other words, I can know momentum exactly in the y direction and x position exactly. Right? So here we have specified that delta px, delta x, is greater than h bar, greater than equal to roughly h bar. There are various forms of it, sometimes h bar by 2 and variations you find. But the idea is that you can't specify both the x direction momentum and the x coordinate with infinite precision simultaneously. You can use delta py there, you may know that exactly, but not delta px and delta x simultaneously. So this is what is known as Heisenberg's uncertainty principle, another principle that we will make use of. I'm just introducing some various concepts here, right? Energy is quantized. Heisenberg's uncertainty principle gives me this relationship. There's another phenomenon that can only be explained by quantum mechanics, and that is called tunneling. All right. Treating an electron just as a particle, there is no way we can understand how this behavior occurs. And what we have here is a finite barrier of height V0. And then there's an electron that is coming and it sees this barrier. Let's say the electron is here, it comes here. And we call three regions A, B, and C. The electron comes to this barrier and is going to try to go across to C. What would it need to do? Common sense. I'm not asking quantum. It has to get up over there and go over this barrier. Right? If it's a particle, it will come and it has to have enough energy to go over that. And if the barrier is high, then the probability of it coming on this side is very low. And if the barrier is semi-infinite, we can practically treat that there is no chance of finding it here. The width of the barrier is given by A as before. So classical mechanics tells us that for a finite width and finite height, if it's high enough, the probability of finding the electron in C region is practically zero. But in quantum mechanics, we see that there is a finite probability for the electron, what we will use the term, to tunnel through. So instead of going over it, all right, it has to go through it. The simple common day analogy is, I am on a journey from Jammu to Kashmir. I'm sorry, Jammu to Srinagar. Yeah? Big mountain in between there. I forget what it is, the range, exact range there. I would have to cross over that mountain. Instead of that, what have they built? A nice tunnel for us. I went through it many years ago. What is the name of that tunnel? It's a pretty long tunnel there. Maybe nowadays you're not allowed to go there, so, but you wouldn't know. But it's a good long tunnel there between, it's gone under the mountain. So there's a finite probability for me to get to Srinagar. If it depended on my mountaineering abilities to get over that mountain to get to Srinagar, the probability is practically zero, right? So I'm behaving like a quantum particle by tunneling through from Jammu to Srinagar. All right, how do we understand this idea of tunneling? When we treat the particle electron as a wave, the only possibility for psi to be equal to 0 is what? Where potential energy is infinite, right? That's why we said in the case of confinement within the well, that outside the well there was probability of it being not there at all. But since my barrier here is finite, that immediately suggests that there is some probability, however small, of finding my electron in here. In other words, psi is non-zero because of the finite nature of this barrier. All right? So classically speaking, the particle is either here or here or here. But in terms of quantum mechanics, because we're talking of a wave, the wave function has a non-zero value because of the finite nature of the barrier. So in this case, psi is non-zero in region B. Okay? Within the barrier, psi has a non-zero value, and so on into C region also. So what we will do is that we can write up, I'll draw it again so that I don't mess it up. If we treat it as a wave that is coming, there is some, I'm not going into the details, there is some finite probability of finding it, the wave within here, and there is also therefore a finite probability of finding it in here. Part of the wave is, this is the incident beam, incident wave, okay. This is the transmitted wave, and there may be a reflected component in this direction. And the regions are defined as before as A, B, and C. I won't go into the details, but we can write wave functions, approximate wave functions for each of these regions, which are just as before as for the other cases. For this region, it's an exponential behavior, sum of two exponentials, but we won't go into that. I just want to say how it comes about and draw its practical use rather than go into its solution. Okay, this is the case we have when we treat the electron as a wave. For a wide barrier, the solution with appropriate boundary conditions. So we will have a psi, let's say for the A region, psi for B region, and psi for C region. Okay, because there is a finite probability of the wave being in any of these regions now. And applying the boundary conditions, we get a solution. And from the solution we can get that T, which is known as the transmission coefficient, excuse me, transmission coefficient, which is the relative probability of the electron tunneling through. T, the transmission coefficient, is the relative probability of the electron tunneling through, is given by T is equal to T naught exponential minus 2 alpha times A. Alpha is some constant there. And T naught has an expression which I'll give you in a second. T is equal to T naught exponential minus 2 alpha A, where T naught is equal to 16E V naught minus E by V naught squared. V naught being the height of the barrier. What we immediately notice when we go to this, the transmission coefficient will be highly sensitive to the value of A, right? If A is small, T is large, exponential minus that term, right? So the smaller is A, if you change it very slightly, then there is a much higher probability that the electron will tunnel through. Correspondingly, R, which is referred to as a reflection coefficient, is given to us by 1 minus T. Basically, there's two things that could happen to that wave. If part of it is, and the probability is that it will go through, then the other probability is that it will be reflected, and so the probability is simply given by 1 minus T. A very practical application of this is what is known as scanning tunneling microscopy. This is made use of in a number of devices, the idea of tunneling, but a very vivid and practical demonstration is done in '86. The guys got their Nobel Prize for this, scanning tunneling microscopy, where a tip of some conducting material, very fine tip, is brought close to a surface. And when we say close to, we are talking of dimensions that are close to atomic dimensions. So there is a value A, how close it is brought by means of appropriate control mechanisms. And when we apply a bias across these two, or even in the absence of a bias, there is a finite probability for the electron to tunnel through this gap. Okay? Here there are electrons, here there are electrons, here is my barrier. So if you look at it, think of it as if the barrier is like this. and I'm here and I want to get here, it has to get across this barrier, right? So the air gap in between there is my barrier. Even in the absence of a bias, there is a finite probability for the electron to actually cut across this barrier based upon this. So by controlling either how much current is flowing I can measure, I can determine what is the change in the height, right? Because small change means the current is changing exponentially. So if I can measure the current flow through the circuit, that gives me point by point at an atomic level information about the topography, how the surface is changing, right? And if I of course apply a bias here, the current flow is much larger, and then the change in bias and all we can control and so on. So this can give me a sort of a map of the surface at atomic level. Okay? There are variations of this, but this is fundamentally what is used for conducting samples. In insulating samples, it's a little difficult to do because current will not flow through the insulating sample as well. But for conducting samples, this is routinely done. Though now even for insulating samples, there are options that are available to do STM. So that's a very practical application of what is called scanning of the phenomenon of tunneling. We can extend our ideas here to 3D. Or electron in a box instead of in a well. So basically we are extending the idea to 3 dimensions. I'm not going into great detail here either. But basically instead of having simply A as my lateral width, now I have a box with dimensions A, B, and C. So correspondingly I'll have an equation that will look something like this. The partial derivative with respect to A of the the second derivative with respect to to x with respect to y and with respect to z plus the 2m by h bar E minus V psi is equal to 0. So once I've gone into 3 dimensions, we're talking of electron confined in a box. And the solution gives me, I get the psi x, psi y, just the spatial components because we're talking of the time independent case. And therefore the total wave function will be given by psi x, y, z is equal to A sine k y y sine k z z, where A is a constant and the k's are also constant. So now instead of simply one k which we dealt with in the one-dimensional case there, I have 3 k values and this is also another constant. This is the wave function that we have. And again using the ideas of boundary conditions and so on, solving this, what we end up with is that these k's, each of them are quantized themselves. Right?
Sir, if T not negative,
Where is that, please?
we are talking about transmission coefficient.
Yeah.
T not equal to 16e, V naught minus e. Is it negative?
It could be. Because you're talking of the V naught minus E, that's why you're asking. Yeah, it could be.
Then what does it imply, sir? Transmission is negative.
So T naught is T naught a probability?
Probability cannot be.
T naught is a probability, so it can't.
I'm not certain on that. Let me check. But if the idea is that you get a negative probability of transmission, the idea is no. Okay, I'm not sure how that is set up exactly, but you will not get a negative transmission probability. Because of the finite nature, there is a finite probability which is a positive term. It can't be a negative term. Okay, it's probably something to do, I didn't pay much attention to that when I was writing my notes, probably something to do with the way we define the E, whether it is with respect to the bottom of that. So in which case V naught minus E may turn out to be a positive number. Right? Because if E is defined with respect to the bottom, you can't see it there anyway now. Yeah, if E is defined as this is E, so then you will end up with a positive term. So it has something to do with it. But the transmission probability is not a negative number, that's for sure. Okay? That was going back to the tunneling idea. I got lost because suddenly you said T naught. I was thinking, where was I? Anyway, coming back to this idea of the electrons in a box, we have now 3 integers, nx, ny, and nz that emerge. And accordingly then, my energy is quantized. You can call it nx, ny, nz, or n1, n2, n3, whatever you call it. So now I have these 3 numbers. And effectively then, my equation becomes, for the quantization, okay, which for a square box simply comes out to be okay, if A is equal to B is equal to C, then we can write n squared is equal to n1 squared plus n2 squared plus n3 squared. Okay? This is for a square box. So the idea is again that we have quantization, but this time we are dealing with 3 quantum numbers instead of 1 that we had there. Now I've got 3 quantum numbers, each of which can have values 1, 2, 3, and so on. E111 is the lowest level or the ground state. But when we come to E211 and we look at the energy, E211, E121 and E112 have the same energies, because that square of the terms, right, n1 square plus n2 square plus n3 square is the same for each of these 3 cases. In other words, there are 3 possible levels, all with the same energy. So we call this a degenerate level. And this particular level is supposed to have 3-fold degeneracy. We can discuss what these quantum numbers mean in a real situation, say for hydrogen, and we will get the different quantum numbers n, l, m, l, and there is a 4th one called spin, which I'll take up later in the next class. I'll wrap this up because there's a little more I'd like to cover. Okay, but we can have that when this is simply applying to electrons in a box. But if I take up a real situation, say for example a hydrogen atom with 1 electron revolving around a positively charged nucleus, then the solution, because it's a symmetric case, yields 3 quantum numbers just like this, but in that case we call them the principal quantum number, the or angular momentum quantum number, right, and the orbital, and then we have spin here. So these 4 things are there. The spin unfortunately does not arise from Schrodinger's equation. That is derived from other sources, but it also is required to explain everything. But these 3 numbers are equivalent to what we are seeing are these 3 numbers here that we have from simply looking at an electron confined in a box. I can take that up later. And there's one more important principle, so that we may have maybe the next lecture. I was hoping to finish off this idea of review in one lecture, but there's just enough maybe I'll touch in the next lecture before we dive into the next topic. Pauli's exclusion principle, which is very important for our use. Okay, we'll stop with that.